some of the strange consequences of quantum theory and parallel universes and the like. So please direct your applause to Jess Werk.
Can everybody hear me? Yes. Okay. If you can't hear me, just raise your hand and I'll try to speak up.
Do you want me to do the mic?
I was going to use the mic, but apparently it distorts your voice and it's not the best. So as long as people can hear me, are people in the back are okay? Okay. So I'll just try it without the mic. The title of my talk is Tales from the Multiverse, Infinite Alter Egos, Parallel Universes, and Other Disconcerting Astrophysical Predictions. And first, I want to start by saying none of this is anything that I've been able to come up with on my own. They're not my ideas. I'm not researching this even. And so a few sources were absolutely invaluable when collecting data and ideas to present to you. And in particular, an article by Max Tegmark. And the one that I'm listing here is a little bit complicated for just the regular reader. There's one in Scientific American that's also called Parallel Universes that's quite good. And these are both available for free on the internet. So I urge you to read them if you're interested in learning more about parallel universes, the multiverse, which I'm going to use interchangeably. I hope nobody's bothered by that. The term multiverse is sort of weird, and I don't know if anybody here has heard it before, but it basically, instead of universe, which means, I guess, one world in which we live, the multiverse is just a set of these universes. So, Colin Bruce has a good book. I have it here. It's called Schrodinger's Rabbits. And this book is aimed at people that have no physics background. And it tries to explain the many-world interpretation of quantum mechanics. And it does so using very weird, quirky sort of examples like shooting chickens out of cannons at double slits and interference patterns of chickens. And it's a fun read, so I recommend it. And I also want to put up a legal disclaimer since I'm going to be talking about things like quantum suicide and, you could take some of the ideas that I'm going to put forward here and take them a little too far such that you might end up injuring yourself. And I don't want to be held responsible for that. But that said, another actual disclaimer is that I study star formation in galaxies with telescopes and look at images and write computer programs, and I don't generally think about parallel universes, and so this has been really fun for me to read about, and I'm avidly interested in parallel universes, but I'm probably going to tell you something that might not be quite up to date, that might be a little bit wrong, and I'm definitely going to confuse you. Actually, I had a conversation with a fellow cosmologist tonight, and he said something that made me feel better. And so basically, if you're not confused by this talk, then you just don't understand and something is wrong. So, great. Prepare to be confused. So I want to start this talk by just giving you a little bit of perspective on how we have thought about the universe as human beings over the course of history. And our picture has evolved quite considerably. Over 1,000 years ago, and for over 1,000 years, people genuinely thought that the Earth was the center of the universe, in a sort of geocentric, Ptolemaic model. And, there's the sun, it orbits around the Earth, but there's not much else in this model. And really, Copernicus revolutionized the way that people thought about the world, in that he just basically said that there's this solar system, and the Earth is one of, 9 planets. I don't know if at the time they knew that there were 9 planets, but part of, a set of planets that's orbiting around the sun, and that's the universe. And then you can see in this cool historical image that there were something that's called fixed background stars. Nobody really knew what they were, what the distances to them were. And so then in the 1700s, William Herschel measured very accurate distances to stars, and the idea started forming that maybe our sun was one of many, many suns in a sort of conglomeration that might be rotating, sort of nebulous, and what we now think of as the Milky Way galaxy. And of course, it seems odd now to us when we have things like the Hubble Deep Field, which shows that there are billions of galaxies in the universe. But back in the 1920s, people genuinely had no idea what these, little sort of nebulae that appeared on the sky were. And there was this great debate, the Shapley-Curtis debate in the 1920s, where, there were two sides of an argument. One side, rigorously defended, was that these nebulae were actually part of our galaxy. And our galaxy is just an island universe. And our galaxy, that might be it. That's the whole universe. And of course, Hubble came along, not the telescope, but the person, the actual person, and measured distances to galaxies. Galaxies are expanding away from us, Cepheid variables, and basically, we live in a universe with many, many galaxies. And now, something called WMAP, which is a satellite up in outer space that measures the temperature of something called the cosmic microwave background, which is basically relic radiation that was emitted 380,000 years after the universe was born. It measures these very, very slight temperature differences. This is a temperature map, and it shows that the universe is extremely uniform in temperature on large scales. So these temperature variations are within one in like 100,000. So very, very small. So we also know from supernovae studies and measurements of things called anisotropies in this, and I don't want to get into it, that the universe is topologically pretty flat, at least as close to flat as we can measure, very, very precisely out to an extremely large amount of decimal places, that space might very well be infinite. At least, the current cosmological concordance that astronomers agree on is that space is flat, space is infinite, space is expanding faster and faster, and space is sufficiently uniform, and there's no real structure beyond 10 to the 24th meters, which is a huge size. So the picture of the universe today is one that's very different from the geocentric universe, where you've just got the Earth and the Sun orbiting around it. Basically, you've got this Big Bang, and then the universe, space stretches out exponentially fast in something that's called inflation, which I'm going to return to a little bit later. And then through various complicated physics, so there's cooling, gravity, structure forms, stars form, galaxies form, and we get the universe as we see it today, which is that the Earth is orbiting around a star that's one of billions of stars, and a galaxy that's one of billions of galaxies, and an observable universe that's about 14 billion years old. And it's vast, it's huge, and it's mind-boggling. And so here's a nice little plot that sort of represents how, over time, our perception of the size of the universe has changed. And you can see back in ancient Greece, the size of the Earth is sort of the lower limit on the possible size of the universe to be. And then for a long time, the distance to Saturn basically just summed up how big the universe could be. And then you get distances to stars, and then distances to galaxies, and then the cosmic microwave background radiation. And all of a sudden, we have a lower bound on the universe that's absolutely huge, and that's actually even consistent with space being infinite. There's no indication that space stops anywhere, that there's that sort of sign that says space ends here, mind the gap. So now, maybe it shouldn't be that illogical an extension. Maybe we should just keep open minds as to the fact that, our view of the universe is ever evolving. And so now we're going to enter the multiverse.